Today we are talking about windowing and clipping. If you are modeling any object, then the coordinates can start from minus infinity to plus infinity. In this infinite range, in these coordinates, which are normally referred to as the world coordinate system, out of this infinite range, we will normally take a finite portion of this range. Let us say starting from this value, which we will call as x min, and going up to x max, and in the y direction from y min to y max. If we take this finite portion of this infinite world, we will normally like to map this finite portion onto the screen coordinates. So, if this is the size of a screen, let us say this being the 0 0 and this being the maximum in terms of x and y, we will normally like this window to be mapped down to a finite portion of this screen. Okay. Maybe we will take the full screen, or maybe we can even take a portion of the screen. What we would like to do is this portion of the world we would like to map onto this portion of the screen. Okay. So, this is referred to as a screen coordinate system. In this screen coordinate system, the x and the y values will again range from, let us say if we call this as the x viewing minimum and this is the x viewing maximum. Similarly, this is the y viewing minimum, this will be the y viewing maximum and this will be the y viewing minimum. Okay. Now, this finite portion is referred to as the window. Okay, this is a window out of the infinite world. A window is thus a finite portion of the infinite world. This portion is referred to as the viewport. Okay, this is a part of the complete screen on which this window is to be displayed. Okay, so if you have any object inside this window, we like this object to be displayed here like this. Okay, similarly, if you have a line here, we like that line to be displayed here. Okay. When this line is displayed here, its size as well as its coordinates, they will be very different from the size and the coordinates over here. Okay. These coordinates are in what are termed as the world coordinate system. These coordinates will be in the screen coordinate system. Okay. Typically, let us say if your screen has a resolution of 1024 cross 1024, then these coordinates will be in this range between 0 and 1023. Okay, this xy maximum would then be 1023 comma 1023. Okay, so these coordinates will be in this range, but these coordinates can be in minus infinity to plus infinity. Okay, and if they are within this window, they will be in the range of between y min and y max and x min and x max. How do we transform the coordinates of, let us say the coordinates of this point onto this point? We will have some transformations, we will go into the transformations later on. Today what we will see is that let us say in this window, if we have a line which is going like this, or if we have a line which is outside this window, we need to know that this line is outside the window so that we don't draw it over here. Okay, this line should not be drawn on this, because this viewport is supposed to draw only those lines or those entities which are inside this window. Okay, so if we have a line like this, that should not be drawn, and if we have a line like this, this line should only be drawn partially like this. The rest of the line should not be drawn. So we will say that this line should be clipped along this edge. That means whatever is outside this edge, outside this window, that should not be drawn. Is that okay? So that is what we mean by clipping. Whatever is inside, that should be drawn completely. Whatever is outside the window, that should not be drawn. Whatever is partially inside and partially outside, that should be cut along the edges. Okay, if we have a circle like this, only this part of the arc should be drawn. If we have a triangle like this, only this part of the triangle should be drawn. Okay, we do not want to draw anything outside the viewport, obviously. Okay, so we will just see how this clipping can be done. If this is the window, if these are the four boundaries of this window, what we have to ensure is an edge like this should get clipped at these two intersection points. Okay, an edge like this should not be drawn at all. Okay, an edge like this should be clipped here. Okay, only a portion inside that should be displayed. And how do we do that? Let us say if this is the one end point, this is the second end point. How do we clip it along the intersection point? We will need to find the intersection of this line with the line x equal to x min. Okay, similarly, we will need to find the intersection of the line P1 P2 with the line y equal to y max. Okay, for this line, let us say this is P3 and this is P4. For the line P3 P4, we will have to find out the intersection with the line x equal to x min and x equal to x max. Okay, so we have to find all these intersections, and it is very important that all this be done as efficiently as possible. Efficiency is of prime concern, because this clipping is done very frequently, and whenever this clipping is done, typically we will have a number of entities in the world. Okay, so we like to do it as efficiently as possible, so that the clipping should be done fast. Okay, speed is of prime concern. Okay, one way of increasing the efficiency is that if we can know for sure that some lines are outside, that means let us say if we have a line like this, if a line is outside this window, I should not try to find out the intersection of this line with each of the four boundaries. Okay, let us say for a line like this AB, if I try to find the intersection of AB with either of these lines x min, x max, y min and so on. If I find any of these intersections, this exercise is going to be wasteful, okay, because this line is totally outside, and wherever the intersections lie, irrespective of that, the line is not going to be displayed. So the first thing that we normally do is we try to see if a particular line is totally out of the window. If a line is totally outside the window, that is, it is either above the y max line or below the y min line, or to the right of the x max line or to the left of the x min line. At least such lines should be removed altogether. I should not try to clip them or find the intersections with the boundaries. Okay. So the first thing that we will do is identify invisible lines. Similarly, if a line is completely inside, if the line is completely inside, even then I need not find out the intersections. Okay, because the line is inside, there is no point in finding out the intersections. I have to draw the complete line anyway. Okay, so I will again try to identify completely visible lines. Okay, and only for lines which are partially visible. Okay, lines which are partially inside the window and partially outside, we should try to find out the intersections with the edges of the window. Okay, and then for partially visible lines, we will find out the intersection and so on. Okay, for this we will have a different set of steps. Okay. How do we identify whether a line is completely visible or completely invisible? As I said, one way is that lines which are totally above the y max line will always be totally invisible. How do I check whether a line segment AB is totally above the y max line? I will have to compare the y coordinates of the points A and B. Okay, so I can say if y of A is greater than y max and y of B is also greater than y max, then the line is invisible. Similarly, I can have constraints for each of the 4 lines. Okay, so if y of A is less than y max, y min, and y of B is also less than y min, that means the line is somewhat like this. Okay, even then the line will be totally invisible. Instead of checking for constraints like this, checking such constraints a number of times can become slightly messy. Okay, instead of that, we use what is called as a 4-point code. With respect to every line, let us say if we take a point here, okay, if we take a point here, now this point is to the left of the line x min, okay, it is above the line y min but below the line y max. So with respect to every point, with respect to every edge, we will give it a 1-point code. Okay. So for this point we have 1, 2, 3, 4. Since this point is to the left of the x-min line, we will give it a code of 1. Okay. If it is above the y-min line, we will give it a code of 0. It is below the y-max line, we will give it a code of 0. Okay, and it is to the left of the x-max line, we will give it a code of 0. Okay, so if any point is to the left of the x-max line, okay, mind you, the visible portion is also to the left of the x-max line. Okay, if any point is to the left of this x-max line, corresponding to that we give it a code of 0. If this point was to the right of the x-min line, we will again give it a code of 0. Okay. So with respect to x-min, x-max, y-min and y-max, with respect to each of them our code will be either 0 or 1. If we are to the left of x-min, we will give it a code of 1. If we are to the right of x-min, we will give it a code of 0. If we are to the left of x-max, we will give it a code of 0. If we are to the right, we will give it a code of 1. If I take y-min, if I am below y-min, then I will give it a code of 1. If I am above, I will give it a code of 0. Similarly, y-max, if I am below y-max, I will give it a code of 0. If I am above y-max, I will give it a code of, if I am above y-max, I will give it a code of 1. As a result, if a point is inside this region, it will get a code of 0, 0, 0, 0. Okay. If a point in this is in this region, the point is below y-min, so it gets a code of okay, let us say this is for y-max, this is for y-min, x-max and x-min. So if this is for y-max, it is below y-max, it gets a code of 0. It is above, it is below y-min, it gets a code of 1. Okay, it is to the left of x-min, left of x-min means 1, and it is to the left of x-max also, so it will get 0. So this code I am using for the first bit, I am using with respect to x-min, this I am using with respect to x-max, this I am using with respect to y-min, and this with respect to y-max. Okay. If the point is in this region, what code will it get? The first bit with respect to x-min would be 0, with respect to x-max will also be 0, with respect to y-min again we are on the wrong side, so it will be 1 and this will be 0. Okay. If you are here, with respect to x-max will be 1, this will be 0 and this would be 0, 1. Okay, and this will probably be 0, 0, 1, 0. Okay, if you come here, then respect to y 1, 0, 0, 1, and this would become okay. So in these 9 regions, the point will get a different code. If the point is here, it becomes 1001. If it is here, it gets 1000, and so on. Okay. Now, if one point is here and the second point is here, both of them will get the code of 0001. If one point is here and the other point is here, this will get a code of 0101, this will get a code of 1001. Both these points are to the left of x-min. Okay, so the bit corresponding to x-min will be 1 for both of them. Okay, so if I take any line segment and out of the 4 bits, any one bit is 1 for both the endpoints. Okay, that would mean the line is totally outside the window. Okay, if I take a point here and a point here, in that case I get a, with respect to y min, both the points are lying below. Okay, so y min, so this third bit here and the third bit here, both will be 1. Okay, so if I take the code for point 1 and the code for point 2, okay, I take the intersection of these codes. Okay, the intersection of these codes has a 1 at any location, or the intersection of these codes is not equal to 0. In that case, the line segment will be totally out of the window. Is that okay? So if the code for point 1 intersection of the code for point 2 is not equal to 0, that means line is invisible, completely invisible. Okay. Similarly, if I have a point here and a point here, then the code for both of them has to be 0000. Okay, so if I say that the code for point 1 union with the code for point 2 is equal to 0, okay, then the line is completely visible. Okay, if the line is inside, then both the endpoints will have a code of 0, therefore the union will be equal to 0. If the line is to one side of either of the 4 edges, then the corresponding bit will be 1, and therefore the intersection will not be equal to 0, and then the line will be totally invisible. Okay, and these bits can easily be set for each point just by comparing them with the x and the y coordinates of the edges. Okay, so by using this the 4-bit code, okay, this is a 4-bit code. By using this 4-bit code, we can very easily check whether the line is completely invisible or whether the line is completely visible. Okay. Of course, there will be some cases like this. Okay, if we take this 0100 and 0010, their intersection will be equal to 0, but even then the line is completely invisible. Okay. In such cases, these checks are not going to result in any decision. We cannot decide on the basis of these checks that the line is invisible. Only when the intersection is not equal to 0 will the line be invisible. Okay, only when the intersection is not equal to 0 we can say confidently that the line is invisible. But if this condition is not satisfied and this condition is also not satisfied, then the line can be invisible or the line can be partially visible. Okay, whether the line is like this or the line is like this, we can decide that only by finding out the intersection points. Okay. So this 4-bit code will help us in weeding out those lines which which satisfy either this criteria or this criteria. Okay. Any questions up to this point? Okay. Then for the other lines, okay, for lines like this, how do we go about clipping these lines? The first is we check for these lines and then start finding out the intersections. Okay, so if I write it crudely, the first step is find 4-point codes for P1 and P2. We are trying to clip the line segment P1, P2. Okay, so we will find the 4-point codes for P1, P2. Then we will check for these conditions. Let us say condition 1 and condition 2. Okay, we will check for these conditions, condition 1 and condition 2. Okay, so I will just write, if condition 1 is satisfied, then line is invisible, neglect it. If condition 2 is satisfied, then line is visible, draw it. Okay. Otherwise, what will we do? We find out the intersections of P1, P2 with the window border. Okay, and check which part is inside and which part is outside. Okay, we will have to find out the intersection of this edge with all the 4 edges, all the 4 edges of the window. We will get one intersection here, the other intersection here. We will say that these 2 intersections are outside this line segment, so we will ignore that. We will find out this intersection and this intersection, and then decide that this line is outside, this line is inside, and this line is outside, and we will finally display this edge. Okay. So in this 4th step, we will have to find out the intersection with each of the 4 edges of the window and check as to which part of the line segment is inside and which part is outside. Okay. This is one clipping algorithm for line segments. Okay. Any questions about this clipping algorithm? We will just modify this clipping algorithm to increase speed further or to make it more efficient. Okay. Any questions about this clipping algorithm? Okay. We will now see a clipping algorithm which is attributed to Sutherland and Cohen. Sutherland and Cohen are the names of two scientists who have developed this algorithm. Okay. Now, the problem of the previous algorithm that comes is that when we have a line like this, okay, we have to find out the intersection of this line with each of the four edges of the window. We will first find out, let us say, this intersection, okay. We then also have to check whether this intersection is inside the line segment or not. Okay, well, since this intersection is outside, is really not relevant. Okay, only an intersection which is inside this line segment is going to be relevant. Okay. Similarly, at this point, this intersection is also outside this line segment, so that is also not relevant. In order to take care of all these, what we can do is, let us say this is our clipping edge, okay, and we have a line to be clipped which is a line like this. Okay, I call this as the correct side of the clipping edge. This is my clipping edge. And this is the wrong side. Okay.
The correct side is the visible side.
Again, please.
The correct side is the visible side.
The correct side is the visible side, and the wrong side is the wrong side. Okay. So if I am considering this as the clipping edge, the right hand side is the visible edge or the correct side, and the left hand side is the wrong side. Okay. Now, if I have a line segment whose both the endpoints are on the correct side, then no clipping has to be performed with respect to the clipping edge. That's straightforward. Similarly, if I have a line segment which has both its endpoints on the wrong side, even then no clipping has to be performed with respect to this edge. Okay. Only when I have one endpoint on one side and the other endpoint on the other side. Okay, I have one endpoint which is P1 which is on the correct side and P2 which is on the wrong side. Only in that case do I need to perform the clipping. Okay. So in the Sutherland-Cohen clipping algorithm, we will perform clipping with respect to each edge separately. Let us say this is my edge number 1, this is my edge number 2, this is my edge number 3, and this is my edge number 4. Okay. I will first perform clipping with respect to edge number 1, and I will check whether both the endpoints are on the correct side or both of them are on the wrong side. If both of them are on the correct side, no clipping has to be performed with respect to edge number 1. If both of them are on the wrong side, again no clipping needs to be performed, the line can be ignored. If one point is on one side, the other is on the other side, I will find out the intersection and the line from the point P1 to this intersection point I. This is the line we are interested in. Okay. So just write down this algorithm. we'll repeat with respect to each window edge. The first thing is okay, check whether the line is completely visible or completely invisible. Okay, that means both the points are on the correct side or both the points are on the wrong side. Okay. If either of the two condition is satisfied, then we can take action accordingly and complete and come out of the algorithm. Okay. Otherwise, what we will do is CS is for correct side. I just explain what we are doing. What I said is, if P1 is on the correct side, continue, else swap P1 and P2. In this case, P1 is on the correct side, P2 is on the wrong side. Okay, there is no problem. But if my line segment was like this and this was P1 and this was P2, P1 is on the wrong side and P2 is on the correct side. I want to exchange the points P1 and P2. I want to call this as P1 and this as P2. Okay, I want to call the point on the correct side as P1. So that when I find out the intersection from P1 to the intersection I, that point I will take as the clipped segment. If this is P1, then from P2 to I will have to take P2 to I. I don't want to do that. I want to take from P1 to I. Okay, so this is P1 and this is P2. I will swap P1 and P2 and still take the line segment from P1 to I. Okay. So if P1 is on the correct side, continue, else swap P1 and P2. Okay, and then find the intersection of P1 P2 with the edge, with the clipping edge, and clip the line segment P1 P2 to P1 I.
Sir, why is the swapping necessary?
Again please.
Why is the swapping of the points P1 and P2 necessary?
Okay. If I don't swap, what I have to check for is which point is on the correct side and which is on the wrong side. If P2 is on the correct side, then the clipped line will be P2I and not P1I. Is that okay? So I'll have to keep track of whether P1 is on the right side or P2 is on the right side. I don't want to keep extra track of that. Okay, I'll just check for that and swap them and make sure that P1 is on the right side. Okay. So after this step 2, I know for sure that P1 is on the correct side. Okay, and then in step 3, I just find out the intersection of P1 P2 with the clipping edge and the line will get clipped to P1i. Okay, and then I'll take this line and repeat it and clip it with respect to the remaining 3 edges. Okay, so first I'll repeat this whole process with respect to edge 1, then with respect to edge 2, and so on, edge 3 and edge 4. Okay, the first step is check for completely visible or invisible line. If you expand this step out, if the line is completely invisible, then the clipped line itself is P1 P2. Okay, and then this clipped line P1 P2 will be passed on to the next edge for further clipping. If the line is completely invisible, in that case the line to be passed will be a blank line. No clipping will be done after that because the line is totally invisible. Okay, so if the line is completely invisible, my clipping algorithm can end here. If the line is completely visible, then this clipped edge has to be passed on to the next clipping edge, and the process will have to be repeated for each of the edges. Okay, so this algorithm is called a Sutherland-Cohen algorithm, Sutherland-Cohen clipping algorithm. And the important thing in this algorithm is, first, clipping is done with respect to each edge separately, and secondly, we are making sure that the point P1 is always on the correct side, so that it becomes easier to say that P1i will always be the clipped edge. Otherwise, we will have to decide whether it is P1i or P2i. Okay. Any question about this Sutherland-Cohen clipping algorithm? Okay. Continuing with clipping further. So far, we have been talking of clipping of line segments only. If instead of a line segment, if we have, let's say this is a clipping window, and if you have curves, okay, if you have a curve like this, and that curve has to be clipped, then clearly the algorithm that we were using so far will not be valid for this curve. Even if I take a simple curve, a simple arc like this, okay, even though both the endpoints of the arc might be inside, a part of my curve can still be outside. Okay, same algorithm will not work. The second problem is that if we have regions, okay, or an area to be clipped, an area can be defined by, let's say, a polygon. We want this area to be clipped. Okay, we like to clip this to this portion. Okay, so if we have a polygon given as a list of points, a list of vertices, we like to be able to clip it and find out the clipped polygon. Okay, so with respect to curves, the way we will do clipping for curves normally is that we will divide this curve into a sequence of small line segments. Okay, for display of curves, they are normally approximated as a sequence of line segments. Okay, and then once it is approximated as a sequence of line segments, we will do the clipping of line segments. Okay, so the curves, they will be reduced to lines. Okay, and if you have a closed region bounded by a polygon, if you want to do the clipping for polygons, then we will have a special algorithm for that, which we will see in the next class. Okay, how do we carry out a clipping of polygon so that we can get a clipped polygon? Okay, a polygon, as we have seen earlier, is a list of vertices P1, P2 till Pn. We want to clip this and get a list of vertices, let's say Q1, Q2 till Qm. where this is the clipped polygon and this is the original, P1 is the original polygon. How do we do this? That we will see in the next class. For curves, we will normally approximate a curve by a set of lines and then do the clipping. Okay. Any questions on clipping that I have covered today?
Couldn't we equivalently do it by building in this clipping thing in our elementary plot the pixel construct? Like we could check for every pixel that we are doing. In the case of a curve also, after you are splitting it into lines, most probably your line will be consisting of just 3 or 4 pixels. I mean, in the case you want greater resolution. In the best case, you will want a maximum resolution.
Yeah.
So your line would consist of 4 or 5 pixels at max.
Okay. If you look at this window, we say that this window is a finite portion of the infinite world. Okay. If you want to do the clipping at the time of displaying the pixel, okay, you decide whether that pixel is inside or outside. Just imagine some curve or some entity which is at a very large distance. You also have to display that and then find out the pixels which will correspond to that. Okay. The idea of clipping is that whichever portion is outside, you will not try to write down the, or you will not try to run the display algorithm for that. Okay, if you try to run the display algorithm for that, you will end up doing a lot of wasteful computation. This portion might be, let's say, only 1% of your complete set of entities you have. If you have a, let's say, an entity over here, no point finding out which pixels will correspond to this circle and then for each of those pixels saying that those pixels are outside the window.
But then for each of the line segments, we'll have to do that anyways, as of what we are doing now.
What we will do is, we will divide this into line segments. Initially it can be very coarse and find out which line segments are inside and which are outside. If we find out that the complete curve is trivially outside, we will not bother about it. Okay. The other thing is, for entities like curves, I mean for entities like circles, we can easily find out the bounds of the circle. If those bounds are completely outside the clipping window, we can ignore that circle. Okay, we need not even try to display that or clip that. Okay. Our basic idea is that we'll try, in clipping, we'll try to remove as many entities as possible without displaying them. Okay, because we know the display is slow. Okay, because in display you are going to compute the details of each and every pixel. And in fact, if you remember, in some of the display algorithms, we are using space which is proportional to the number of pixels. Okay, so if we are talking of an infinite space, we really can't do that. Okay, we cannot have infinite number of pixels and decide the intensity of each pixel and so on. We will have to, if we try to compute the pixel corresponding to each of these points, depending on the number of entities that we have, that can also become very expensive. Okay. So first thing we do is, we try to see whether this curve has any portion common with the window. If it does not, we will ignore that. If it does, only then we try to do the clipping for that. Okay, and for that we will approximate it by a set of lines and then do it. So then we know that some portion is going to be common. Okay, even let's say for a curve like this, if we start finding out the set of pixels that will correspond to the invisible part of the curve, we will have to find out, for each of these pixels we will have to find out whether the pixels are inside or outside. That is going to be wasteful. Instead of that, we will divide this into a sequence of line segments. Okay, normally what we do is, we initially start with a very coarse division like this. Okay, and only if we feel the need, we will start bringing them closer. Okay, if we feel that, let's say from here to here, a part of the curve is going to be inside, then we will subdivide it further, and so on. We will be seeing more of this in detail in some of the later topics. So I think that at that point it will become much clearer. Any other questions? So that's all for today then. We'll